Today we are going to do section 6.9, the hyperbolic functions. Okay, this is on page 745. What are hyperbolic functions? They are some kind of a combination of e to the power x, adding or subtracting. For example, as you can see in your book, sine h of x is just e to the x minus e to the minus x over 2. And cosine h of x is similar, except it's a plus. Now, why are we calling some combination of hyperbolic functions? It's a tradition in mathematics well, somebody did it. And then and then they are they're very happy, and once they found and they defined it this way, then they beat it around and discover properties about the hyperbolic function. The sine hx, first I want to explain why they're called hyperbolic. The reason is, I don't know, there's nothing hyperbolic about them. Normally the hyperbolic functions are things like 1 over x, where they have well, anyway, we'll worry about that later. The point is, there's nothing here except out of the 6 graphs that you can see here, okay, the examples of the hyperbolic functions, there's 6 of them. Out of them, which one looks like 1 over x? Well, 2 of them does, but we really don't care. All right, the rest don't. 2 out of 6 that even look like it. So, but in any case, being that we're not really that interested, because they're just combinations of e, right? So if we want to do this stuff, why don't we just use e? I mean, why do we have to define a new name for an old trick? Part of the reason is because hyperbolic functions has certain qualities parallel to the trigonometric functions, sine and cosine. That's why they are named this way. Okay, we will pronounce it, and they're named after all 6 trigonometric functions. So there is sine hx, cosine hx, tangent hx, etc. However, there is nothing more than there's nothing else that's interesting about them, and they are nowhere near as important as the trigonometric functions, which is why up to this point of the book, this whole time we have never touched the hyperbolic function this whole time, and you're not going to touch it later, okay? For the future calculus, I mean, at least not that I can remember. The only thing that the hyperbolic functions that is useful for is it is good for certain integration formulas. That's the only thing I can think of. Okay, the reason, and then we will see that in a minute. Now, the hyperbolic functions have a bunch of properties that's listed in chapter 1 that is somewhat similar to the trigonometric functions, but I recommend that you don't memorize them unless you have a very unusually precise memory. Otherwise, because they are similar, you might confuse. I feel like they might confuse your memory of the trigonometric functions, which you do need to memorize. Like, they're similar but different, but not identical. See, they might be a negative sign here, or a positive sign there, or something, and we do not. And I do not want you to mess up your trigonometric function memory. Okay, so let's not mess it up. And just, if you ever need to handle hyperbolic functions, look up whatever the relationships are, on the spot. Now, the derivative of the hyperbolic function also mirrors the trigonometric functions. For example, look at the next page. When you take the derivative of sine hx, which doesn't take much, okay, because it's just e of x, and we all know how easy it is to take the derivative of e. It round up, and by the time you're done, you realize that it is just the cosine h of x. And similarly, all the other stuff works out about the same. Okay, after you do some basic algebra, you come up with an entire chart of what is the derivative of the hyperbolic functions. And by the way, I should mention that your book in chapter 1 claims that sine h should be pronounced as sinh, and cosine h should be pronounced as cosh. Yeah, let's not do that, because what are you going to pronounce tangent h? And what about secant h? And worse, what is cosecant h? And then by then, if you were to Google it, they tell you to make the weirdest sound, and we're so not going to do that, because for one thing, we almost never use it. Okay, this is and so here are the derivatives of the the hyperbolic function, and I'm going to skip that. But you can do the examples to just get yourself slightly familiar with how to differentiate hyperbolic functions, which is of course a piece of cake. Okay, it just kicks right up. And as a result, you can also do the integration, okay, if of hyperbolic functions, or some of them anyway, the ones that does have a antiderivative. And that's the next example, example 6.48. Next, the next thing that is more useful is the inverse hyperbolic functions. Well, actually, only some of them or something. Anyway, so once you have a function, you always have the inverse by flipping it over. That is, by drawing its mirror image against the y equal to x line. That's the definition of the inverse function. So all the hyperbolic functions have their inverses, and they all have different domains maybe, and we don't really care. I mean, you just when you need to look at the function, then you check out its domain and see where it's going. But other than that, that is not interesting at all. Okay, so the inverse function looks well, whatever. They look like something. And then the thing is, however, then we try to find the derivative of the inverse functions. And when you do that, what happens is then you come up with something that's very similar to the inverse functions of trigonometric functions. See, for example, if we were to calculate the derivative of inverse sine h, then you apply the implicit differentiation, and then a few lines later you come up with something, right? It equals 1 over 1 plus x. And this is the point where hyperbolic functions actually becomes somewhat useful, because they're inverse functions. Then once taken derivative becomes a bunch of stuff that we can add to our tools of integration. Because so far we have only a few things integration, and that the fact that hyperbolic functions become these things means that we can add a couple more. Basically, we can add this pile of stuff, okay? Which still doesn't cover all the possibilities of integration, but at least this helps, right? If your function looks exactly like that, then you know the antiderivative will be one of the hyperbolic functions. And you notice that the tangent inverse has the same derivative as the cotangent h inverse. And why is that? That's because of the domain, okay? Because the tangent inverse is one of them is defined only in a small area, and the other one is defined outside that small area. So the reason is different is because they're talking about different parts, okay? They have different domains. So so when you do the integration, then you just check where's your x, and then do it that way. Anyway, so please do the next example, 6.49, and then in 6.50, which you do the integration, and then you will probably use substitution. Yep, but that's still straightforward. You're good at that by now. So, but still, do that for the for the heck of it or something. And yeah, and then we come to something called applications. There's no application for the hyperbolic functions, but they did find one thing, okay, that the hyperbolic function happens to be. It's a very specific instance where the hyperbolic function, the graph of the cosine h, happens to look like that. And by that I mean exactly, some kind of a hanging object like that. And you can, if that's the case, the graph of the cosine h can simulate it exactly. It's like the best simulation. You might think, well, doesn't that look like y equal to x squared to you, or something like that? But this is even better. Okay, is a very precise imitation of the hanging rope. So if you ever need to calculate the hanging rope for some reason, then the cosine h can come in handy, and that will show in example 6.51, which so please do that as your homework as well. And then and that's that. Now for homework of this section, I have chosen 3 problems. The homework is problem 6, 413, 417. 413 has answered in 2 parts. Maybe it's because of the tangent, I think. Anyway, and then 417 and 418. So please finish the homework. Yeah, only 3 problems. And then I will talk about it when you get back. So now that you have finished with the homework, I want to talk about all of them. There are only 3 problems because the reason I only picked 3 because there are only 3 of them that's integration, which is the only thing that the hyperbolic functions are good for, in my opinion. So then let's look at 413. The integrations are all fairly straightforward, at least these problems are. And so I will just show you what I did, okay? For 413, you're supposed to integrate dx over a squared minus x squared. And there's something that's similar to this. You just have to plug the a out, okay? And once you take an a out and then do a u substitution and stuff, then the answer becomes the cotangent right away. However, if you were to look at the answer sheet, then you notice that this particular form of stuff, actually there are 2 things that become that, okay? There's, see, 1 over x, there's tangent h, and then there's inverse, then there's cotangent h inverse. Why is that? Because it depends on the domain of x. That is, I found out that what happens is that the answer comes in 2 parts. A equals to the cotangent h. Did I write inverse here? I'm missing the inverse, aren't I? Well, don't forget to write the inverse in here. Yeah, it's inverse. Goodness. Anyway, I'll write down the inverse later. But anyway, so it's why is that 2 parts? It's because when x is less than the a, then it's on the inside is the cotangent h. Inverse, and then when it's bigger than a is the tangent h inverse. So it's a 2-part function. Well, which your book didn't do. I think your book only gave like the tangent one, which is why how I noticed. When I came up with a cotangent, then I realized, oh, I forgot the answer is the same. So you have to pick one. And in this case, we'll pick all of them because our original x is defined for all values, right? Because it's x squared. So we really don't care if it's negative or positive. With the only exception, of course, is x cannot be a because then we'd be dividing by 0. So that's that. And then the next problem I want to talk about is problem 417. Yeah, well, again, that is a very simple thing once you realize what to choose for the u substitution. You just choose u equal to e to the power x, and then plug everything in, and it all fall out nicely. And of course, never forget the c. I see that for this problem, I did put the inverse in. I wonder why I forgot it up here. Well, doesn't matter. Don't forget to put the inverse in. And so that's that. And then the next problem for 18, same thing. Okay, the hard part is just let me move my hand here. Okay, the hard part is just figure out what is u. Well, it's not that hard. Very soon you're going to find out that if you set u equal to x squared, everything will fall into place, and you get that tangent thing again. Yeah, and again, the answer comes in 2 parts. Depending on whether x is bigger than 1 or less than 1, the absolute value of x. And yeah. So that's about it. In fact, we have come to the end of the book, which is very exciting. Okay, so if you have finished the calculus, I congratulate you as I congratulate myself for finishing it. And so please give yourself a reward if you can, and then go to Calculus 2 if you feel comfortable about Calculus 1. If you finish Calculus 1 as hobby and you feel like, well, I did pretty good, but I wish I was better at understanding all the material, then there's nothing wrong with doing it again, going over it again as a hobby. before you get to calculus 2. And so it really depends on how you feel about it. Do you feel like you got an A in this class? You're confident about all the material and you're good for the next class. Or do you feel like, well, I did pretty much okay, but I needed a lot of help on my homework, and overall I could probably do it again. Then it doesn't hurt to do it again. It's like reading Harry Potter a second time. A second time is great. Okay, I've read the Harry Potter series like 20 times, so a second time is good. Okay, you can get a lot of stuff that you didn't see before, and there's not. And being that we are doing math as a hobby here. Okay, this is just a hobby, and what's hobby for? Hobby is for fun. So if you do it a second time, it might solidify your understanding and your familiarity with the material so that you'll be ready to do calculus 2. But otherwise, if you say, oh yeah, I did great, okay, this is all goes pretty straightforward, it's not as hard as I thought it would be, and I am totally ready to do calculus 2. In that case, please do calculus 2. I have already prepared a couple chapters of that stuff. So go ahead and move on to calculus 2, or go back to redo calculus 1 as you feel comfortable with. And so I hope that I thank you for finishing the class with me, and I hope to see you in calculus 2.